Right, in the first session on this, we just looked at those point charges. We looked at how many electrons we need to move to be able to create a charge of so many coulombs, right? Now we're going to look at Coulombs law, right? And Coulombs law, we're going to pop it up. Let me just read what it says here for Coulombs law, all right? And you're going to have it obviously in your own textbook. I've got half a dozen different textbooks from all over, different education systems from all over the world. But fundamentally, the one we've got, you have to learn it. And like I say to all my students, please remember that, a big chunk of the final result isn't the calcs, right? I'm here to show you the calcs and the support and what they mean, and maybe a little even more advanced where we can do it. But what do we do? There's the element of theory that you've got to learn. How you do that, you write it out, say it to yourself, I don't know, have it playing over and over while you're asleep. I have no idea. When we were at varsity and that, people did all sorts of weird things. I truly don't know if any of it helped, but you've got to learn that theory portion of it, right? Very often a good way, maybe as a tip, I don't know, I'm not a learning expert, but as a tip is to, when you're looking at the thing, look at the formula at the same time and understand the linkage between the words and the symbols in the formula and what they mean. So let's look at Coulombs law. It says, the force of attraction or repulsion exerted by one charge on another charge is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. Hold on. If you actually wrote down F equals K Q1 Q2 over R squared, like so, correct? That's the formula. That gets given to you. You could state Coulombs law directly from that. The force between any, there it is, directly proportional to the product of their charges, inversely proportional to the square of the, it's actually given to you. But that's what it says. So you have to know that, right? Let us start off with a fairly straightforward and a fairly simple one, right? Let's say we've got two charges. Here we go, X and Y, and it's like this, right? So we've got charge X over here, and that is 4.6 plus times 10 to the minus 9, which means nanocoulombs. The other one is going to be Y, and that's going to be minus 3.2 times 10 to the minus 9 coulombs. They're nanocoulombs. Remember, we've got these here, and these ones you're going to have to know. Nano, 10 to the minus 9. Okay? Micro, 10 to the minus 6. Milli, 10 to the minus 3. Okay? Those we know. I just remember nano, 9. It's the easiest way. Pico, we don't do, I don't think, 10 to the minus 12. But if we see one, well, we just deal with it. Okay, so let's look at this. They now say, what is the force between these? Right, first of all, we say force is equal to K. Now, what is K? K is 9 times 10 to the 9. K is equal to 9 times 10 to the 9. They will give you units with it. Newtons, square meters, coulomb per coulomb squared, or coulomb to the minus 2. Okay? So the force at the end of the day now is going to be that guy, right? K. Do we have K? Yes. 9 times 10 to the 9. Multiplied by Q1, Q2. Right? In brackets, guys. 4.6 times 10 to the minus 9 times 3.2 times 10 to the minus 9. And it's all divided. The last bit of information they've given us is that they say that they are 30 millimeters apart. Okay? What do we have to do with the millimeters? Change it to meters, right? So we're going to divide that by 1,000. So in this case, my R, okay, is going to become 0.03 meters. So it's divided by 0.03 squared. And we work that out, and the final answer comes to 1.47 times 10 to the minus 4 newtons. Okay? Then the last bit is to say, right, this was plus, minus. Let's draw in our field, shall we? All right. Red, plus was this side, minus, so it goes from plus to minus, and it is attraction. Right? It's a force of attraction between the bodies. That's what we've got. So here we've now solved. Now you might say, my goodness, but that's a very small force. Well, yes it is. It's an extremely small force in magnitude. But consider, what is the weight of an electron? If you go and look it up, you'll see it is incredibly small. 9.3 times 10 to the minus 36 or something like that, right? It's actually on your sheet that you get, right? But, or 31 possibly. So the mass is very small. So if you've got a small force and a very small mass, the result is quite spectacular, because you've got such a small amount of mass that force is moving. Okay, and it's the whole F equals ma again. So that is straightforward. Obviously, the next part of this is where we would have, let me say, all right, they could give us this situation. Okay, they could give us, let's say, plus 5, okay, and let's change it to microcoulombs, and that is charge at point A, and at point B, we've got here minus 3 microcoulombs, and at point C, we've got here minus 7 microcoulombs. So now what is going to happen here? I've drawn my A and my B out of kilter. But let's look at it first. They will say, calculate the resultant force at B. Right. What do they mean? They mean, first of all, they want to know what is happening at point B. So that is the place where we're going to be looking to look at the forces. Let us start with the AB situation. Right. Positive, negative, so our field would be like that, wouldn't it? So we've got a force of attraction here. So we would say this and this are being attracted that way, right? There's a force here and a force there of attraction between those two particles. And can we work it out? Yes. F is equal to K Q1 Q2 R squared, 9 times 10 to the 9 times Q1, 5 times 10 micro minus 6 times 3 times 10 to the minus 6, all over. Now let's give it a distance. Okay, shall we call this 20 millimeters, and maybe this side 30 millimeters? Okay, let's go back to our red force, the red side. What have we got here? This is 20 mil, right? So that's going to be divided by 1000.02 squared. So let's look at what the force is in this case, shall we? It's 9 times 10 to the 9 times 5 times 10 to the minus 6 times 3 times 10 to the minus 6. Okay. Times 10 to the minus 6. Sorry, I put my thing. That's that. Divided by 02. Okay. Is equal to 337.5. Okay. I'll double check that now. Okay. Let me just double check it. Okay. It's 9 times 10 to the, I think I might have forgotten my times 10 to the 9. Okay. 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 Times 5 times 10 to the minus 6 equals that, times 3 times 10 to the minus 6 equals that, okay, and then divide 0.02 equals 337.5. Okay, now it suddenly is not looking that small, is it? Let's have a look at the other side here, and we'll take this one and let's call that green, shall we? So we say here F is equal to K Q1 Q2 over R squared. Let's put in some numbers. K, 9 times 10 to the 9 over there, multiplied by, now the green force, it's a minus and a minus, which means it's going to be pushing away, right? It's repulsion over there, isn't it? They are repelling each other, and it's going to be 3 times 10 to the minus 6 times 7 times 10 to the minus 6 divided by the difference, the distance is 0.03 squared. Okay, let's see what that force turns out to be, shall we? Okay, it's going to be here 9 times 10 to the 9 multiplied by, okay, what's that, times 3 times 10 to the minus 6 equals that, times 7 times 10 to the minus 6 equals that, divided by 0.03, divide 0.03 is equal to 210. Right. Now what is happening here? Well, what is happening is we've got at point B, this is our point that we're looking at, right? Let's put that in blue. This is where we are looking over here now. That's where our eye is focused. What have we got? We've got force over here, the red force at that point. Let's put the red. The red force at that point is which way? It's pulling B this way, isn't it? It's an attraction of 337.5 newtons this way. Then we go and we say, okay, what is our other force? It's 210 in the same direction. So therefore, we've got a resultant force equal to 337.5 plus 210. 337.5 is equal to 547.5 newtons. Okay. To the left, because this point B is going to go shooting off that way, isn't it? Okay. And yeah, it could hit that one, equalize charge, be bounced backwards and forwards. Okay. So that is a resolution to get a resultant force. Yep, FMA would come into that, but we're not going to go there at the moment. Okay. Let's now look at the next one that can be given, which is very often given, more often than not, is let's put the forces, or let's put the charges in different directions, shall we? Here we go. We've got here force, okay, I just want to just take it over here. We've got force, and we say this is 2 millimeters. This is 4 millimeters here. This is point A. This is point B. This is point C. They've told us that at A, we've got a charge of 2 millicoulombs, and it's positive. At C, we've got a charge of 4 coulombs, and it's also positive. At A, we've got -1. It's a negative. Okay? Well, what have we got here now? Okay? Let's just take out that line just so that I can... I just want to put a dotted line there. Okay, over there. Now you can see we've got our charges at C, charges at A, and charges at B, and our distances. The question is, calculate the resulting force at point A. So what do? We go to point A, and we look at the other force acting on it from that point. So let's go with the red again. Let's look at what is B doing to A. Well, this is plus, that's minus, right? So what is B doing to A? It's a force of attraction. So it's going to be, these two want to go that way, don't they? So that's the force there. That's the force due to B. Let's say it's an attraction force. Let's go and look at the green side. This here, these two are positives. They're going to want to push each other away, correct? That's force due to A. Sorry, my bad. That's force due to C. It's going to push it that way, okay? So that one's going to push it away. Technically, we could change this one to F of C, if you like. Okay, the subscript isn't critical in this. What we've got to do is we've got to make sure that we get that first, because that's going to show us which is the horizontal and which is the vertical. Is it up or down, left, right? That's what it's going to show. So now can we calculate that? Well, yes, we can. So let's look at the B first. What is the force between there? It's going to be F is equal to K, Q1, Q2 over R squared. And K, 9 times 10 to the 9, right, times Q1 in this case was going to be, well, it doesn't matter which one of those you take, actually. You could take either one, okay? But let's take that one. 9 times 10 to the 9, minus 1, remember? But we don't worry about the sign. You can use it if you want to, for completeness sake. Times 10 to the milli, minus 3, times 2 times 10 to the minus 3 over, the distance is 2 millimeters, so it's going to be 2 divided by 1,000, which is 0. Right, 1, 2, 3, right, and that's squared. Okay, that comes out and gives us, well, let's have a look. It's 9 times 10 to the 9 is that, times 1 times 10 to the 3 was that, times 2 times 10 to the 3 is that, okay, divided by, okay, is 4.5, okay, times 10 to the 9. Okay, which is pretty huge, actually. Okay. Okay. Then we say, right, then what is the next one? What is our green force here? Okay. F is going to be equal to 9 times 10 to the 9, okay, multiplied by 2 times 10 to the minus 3, which is this force, multiplied by this one, 4 times 10 to the minus 3, all over, this is 4, so it's, if you prefer, 4 times 10 to the minus 3, isn't it? Right. And if we calculate that, we get a force of 4.5 times 10 to the 9. Yep. All right. Okay. Now we can go back. They both come to be the same force. Okay. Okay. 4.5 times 10 to the 9. Okay. What does that mean? Now we can go back to this of ours and we can say, okay, which way is force the green acting? Well, we said the green in this case is going to be pushing me to the left, isn't it? So let's just show that. Okay, the green force is going to be pushing me to the left, and it's 4.5 times 10 to the 9. And the red force? Okay, let's go back and look. The red force was pulling me up, wasn't it? Okay. The red force was pulling me up, in this case, of 4.5 times 10 to the 9 newtons, just for completeness sake. Green newtons. So what have we got? We've back to the old problem that we've had before. We move that one across and we get an R. And we can say that R is going to be equal to the square root of that times 10 to the 9 squared plus the same thing. Okay, all to the power of a half, which is the square root, correct? If you don't want me to put it in terms of the exponent like that, let's put it like that, correct? And the resulting force comes out to be 6.4 times 10 to the 9. 9 newtons. And theta is going to be arctan of basically, right, 4.5 times 10 to the 9 over 4.5 times 10 to the 9, which is that divided by that, because it's that there, right? Which is going to be, okay, and we're going to have arctan of 1, aren't we? And you probably know the answer to that already, 45 degrees. Okay? So it comes down to 45 degrees. So in these systems here, what is the key to it? It's first of all, obviously, once again, physics drawing, put in what you know. Secondly, go to each point and say they want to know at A what is happening, right? So what do? We say, right, at A, I've got a minus and a plus, so they want to pull towards each other. So point A wants to move to B. The next step is to go to C and see what does A want to do now. A is going to be pushed away from it, right? Then we use the equations using the charges and the distances, and we work out what the force is going to be. And fundamentally, it doesn't really matter. We could end up in a situation like this, couldn't we? We could end up with a force pushing me down and a force on the other way of, let's go here, force that way. We could end up with a force this way of 50 sorry, I'm thinking in terms of charge. Let's say 50 newtons that way, and a force acting down of 30 newtons that way. What would we do? Move it across and then get the resultant there. So the force could be that this particle here is being pushed that way, being pushed away. Now, remember, we could also do it. Let's just take another hypothetical situation here. Let's put it back to black. We could also take an A and a B and point C over there, point charges, giving us the details. So Q at A, Q at B, and Q at C, they're all known. They could say, what is the resultant on force C? Well, what do we do now? Well, we do this, don't we? We do exactly the same because it's a recipe. Let us say this is a plus, and that's a plus, and that's a minus. What is A doing to C? The force is going to be in that direction, isn't it? So A is positive, C is negative. A is wanting to move C along that line towards it. So the force we get would be that line, wouldn't it? It's the way it's pulling it this way. Then go and we say, what is our green? This is plus and minus. This one is also going to be a pull this way. So we've got our F that way. Now what do we end up with? Well, this is quite straightforward. We end up with an F this way, and we end up with our red force is now acting at an angle, isn't it? Like that. What do we have to do? We've got the distances here, remember? Let's say BC. Oops, sorry. Let me not use red down there. I'll use it here. AC is known. Okay, similarly, if I put in my green, the distance BC is known. So you can work out what the angle is there. This here, okay, let's just go back. This angle here is known because you would use the distances that you're given to work out the angle using arc sine, arc cos, arc tan to be able to work out the angle, right? Then what would we do? We do what we always do. Component, component, then the green would be added to that one. So we'd have a long one that way. This one would then be up there. So the net would be like that, right? So it doesn't matter. We just follow the same process of solution. Just in this one, it's a slightly more difficult process to do. Okay. The next part of this that we're going to have to deal with is where we now change it to an electrical field strength. Similar processes, similar procedures, just a slightly different way of looking at it. Okay? Because we're going to be moving towards electricity, so we've got to get this electric field strength thing behind us, right? So that's the section we're going to focus on next, is looking at electric field strengths. Why? Because they exist. Remember, these are things that we see in real life. And we actually use, in the next section, I'll give an example where we're going to see it, use an electric field strength. And we'll do that in a few.